Hello, the topic we are going to treat today is Ohm's law and its applications. Ohm's law states that the current flowing in a metallic conductor or wire is directly proportional to the potential difference across its ends, provided the temperature and other physical quantities remain constant. Let's just put that down and see how we can refer to that in solving one or two problems. All right. Ohm's law states that all right, the current flowing in a metallic, okay, flowing in a metallic conductor, okay, metallic conductor or wire is directly proportional. Proportional, right, to the potential difference. Is directly proportional to the potential difference PD, right, across its ends, right, provided that the temperature and other physical quantities remain constant. Provided that the temperature and other physical quantities or conditions remain constant. All right, provided that other physical quantities remain constant. All right. So this is exactly the statement of Mr. Simeon Ohm. That's a well-known scientist. All right. So mathematically, we can put this as thoughts. Mathematically, Ohm's law can be stated as follows. Ohm's law can be stated in terms of mathematical arrangement or representation of Ohm's law can be stated as follows. Let's look at mathematical representation. That is, current is directly proportional to what? Potential difference across its ends. Or we can restate this as voltage, potential difference across its end is also directly proportional to the current flowing. All right? So that's the statement of Mr. Simeon Ohm, Ohm's law. Now, if we introduce an equality sign and a constant, respectively, we arrive at V is equal to K and then what? I, all right? The Ki or Ik, right? So what this means is that the ratio of V to I, the ratio of the voltage, is always a constant. That's what it means. That the ratio of the voltage to current is always a constant, where V represents the voltage, where V is the voltage, all right? Voltage measured in volts, right? Measured in volts. Okay, I is current. Current measured in amperes. Okay? Alright? Then the next one is the letter K is proportionality constant. Proportionality, alright, constant. The proportionality constant known as the resistance. Okay? Known as the resistance. Proportionality constant known as the resistance. As the resistance R. So we call this the resistance R. Okay? So that is it. The next thing we're going to look at is to rewrite this with the letter R, the resistance. So we rewrite, we have V all over I is all equal to what? R. Okay? Or the other way around. Or we have R is equal to V all over I. So this makes sense now. Entirely, okay? We have relation 1, the first statement, relation 2, and relation 3. Actually, the resistance of the circuits, if it is plotted, if we plot the values of V against the values of I, the slope of the relationship is the resistance of the circuit. Alright, so that is it. Now we need to understand something here. Importantly, we need to note that when the resistance is very, very high, current is very, very low. When the resistance of the circuit is very, very high, current flowing through the circuit is very, very low. Also, when the resistance of the circuit is very, very low, current flowing through the circuit is very, very high. I repeat, when the resistance of the circuit is very, very low, the amount of current flowing through the circuit is also very, very high. It's just vice versa. All right. So the next thing we are going to consider is the relationship between voltage and then current. If the values of voltage are plotted against the values of current I, how would they behave? They will behave in a uniform manner, and that uniform manner is known as a Lichtelianal relationship. Okay? It's a straight line relationship. So we look at this graph of V against I, right? Let's see. If we take the graph of V against I, look at what we're going to have. We have a straight line graph. Okay? We have a straight line graph. This is I measured in amperes, and here we have a V in volts. Okay? So that is it, a straight line graph. Whose slope, that is a change in voltage, here a change in current, right? We give, the slope represented by R is this thing, all over all that. That's it. You can see the slope of this relationship give the resistance of the circuit. Very simple. Then the next thing we need to understand here is how to resolve the slope and then arrive at a certain answer. Now, having said that, there are materials that obey Ohm's law, and such materials are referred to as ohmic conductors. So we look at, first one, we look at materials that obey Ohm's law, known as ohmic materials. So ohmic materials are A, copper. We have copper here. There is copper. B, we have silver. Then C, we have aluminium. Okay? All right. And then we can still have D, and so on and so forth. Okay? We can still have D. All right? But at this point, we have other ones. So there are other ones that obey Ohm's law. What it means is that if these things are used as materials to experiment Ohm's law, they will give what? A straight line relationship. That's what it means. And once that happens, that means they obey Ohm's law. However, there are materials that don't obey Ohm's law no matter what. And such materials are referred to as non-ohmic materials. So the second one we're going to look at is non-ohmic. Non-ohmic materials, okay? Non-ohmic materials are A, we have diodes, right? B, we have rectifiers. Then C, hot valve, and so on and so forth, okay? So these are materials that do not obey Ohm's law. It means if these materials are used in experimenting Ohm's law, they will not give a straight line relationship. They will give a kind of curve, a straight line and then curve. So they won't give a perfect straight line relationship. And that is why they are referred to as non-ohmic materials. All right, so that is it. At this point in time, I want to thank you very much for your questions. I really want to thank you for your time. I urge you to subscribe to our YouTube channel at Levi Kingsley. Visit us at our Instagram handle, Twitter, Pinterest, Reddit. Like our Facebook page, and then play us on Likey.